wanted to make this video because I know that we are getting very close to spring break, and I don't want to spend a whole lot of time going over the full depth explanation for this quiz. So please watch it. There are a couple things that you can pick up by the discussion I'm going to have here. Quite a few of you made very similar mistakes. Some of you did not make the same mistakes, but actually did read the question well enough to earn a significant number of points. So let's go over this question. All right, so we have our reaction here where we have C2H2 plus 2 hydrogens yields C2H6. Information about the substances given. So we have our delta S and our delta H. Again, this represents for the chaos, disorder, or order, and this represents the heat of formation. And then over here on the right, we have our bond energies for our single bond, double bond between the two carbons, a single bonded hydrogen, and the bond between the hydrogens itself, and the values there. Part A asks, if the value of the standard entropy change, which is delta S, so again, delta S represents for chaos, disorder, for the reaction is negative 232.7 joules per Kelvin, or per mole Kelvin, calculate the standard molar entropy. Now, we haven't talked about what standard conditions are yet, and we will actually a lot in electrochemistry, but there are two things that go along with standard conditions. The first one is the temperature, which is at 25 degrees Celsius. The other one, which we haven't spoken about yet, which is insignificant for this reaction, is if you're looking at a molar solution, it's a 1 molar solution. So whenever you hear about standard conditions, we're talking about 25 degrees at 1 molar, or the molarity is 1. But that doesn't apply in this case. There are also some other information here that's pretty important and pretty relevant. Gives you the delta S for the reaction. And again, when it says for the reaction, that has nothing to do with these individuals here. It's the combination of all of these that give that value for the reaction. And you'll notice that later on in the question it asks for values for the reaction. So these are the reactant or product information. So please make note. And it probably wouldn't be a bad idea while you're writing down the information, especially when you get to another question that says, oh, okay, well, what is the heat of formation or the enthalpy for the reaction? Probably wouldn't be a bad idea, like in the upper corner here, just like, okay, I'm going to need the heat or the enthalpy of the reaction. I'll need the delta S for the reaction, and eventually I'll probably need the delta G for the reaction. Okay, so, and again, when we talk about that, make sure that we're using the values for the reaction, not for the individual reactants or products. But looking at the first question, it wants to know what is the value for the delta S for the C2H6, and again, knowing where that's at on the balanced equation. So the C2H6 is our product, and that is the value that we do not have. So we want to, again, go to the equation sheet, and the equation sheet says that the delta S is equal to the sum of the products minus the sum of the reactants. And what we're talking about is the values for the delta S. So in that case, what we want to do is we want to find out what those values are. So I'm going to write those values down. So again, our equation is our products minus our reactants, so we'll go ahead and plug in our information. We're actually looking for the product value here, and this again is for our reaction. We have our values that are given from the table, so we have one of the C2H2s, and then we have 2 of the hydrogens. So again, we have to be aware of the coefficient there, that's our multiplier. And then once we take all the math there, it looks like this. We want to isolate our C2H6 there, so let's go ahead and I'm actually going to add the 462 to both sides to get my value for that, and then I get 229.6. Now, be sure that you are showing your units, especially in your final answer, and be aware that generally speaking, when we talk about or look at delta S or entropy, delta S, or the entropy, is in joules over mole Kelvin, because again, where it arrives or where it's at in the equation where delta G is equal to delta H minus T delta S. So we have a little bit different unit, and it is in joules. So it's probably a good idea to know what the units are for delta G and delta H. They're the same. They're kilojoules per mole, where delta S is a little bit different. It's in joules per mole Kelvin. So that requires us to do a conversion if asked to find delta G, which in this case, it's fine to leave it as such. Looking at part B. Part B says calculate the value for the standard free energy change, which is delta G, for the reaction. What does the sign of delta G indicate about the reaction? So again, there's two questions that are being asked in this problem. So it's asking about what is the value, so we want to find out what the value is, and then it asks a second question about, well, what does the sign on delta G represent? Again, being aware that we're looking for the reaction. So just because this is the last value that's in your calculator does not mean that we are going to use that value. And I'd say a large amount of you did use that value. But again, if you're writing your units on here, the C2H6, that is not for the reaction for our delta S. So the equation that we're going to use here, delta G, and again, this is on your equation sheet, delta H minus T delta S. Now, again, we are just now learning about standard. That's why I told you what the temperature was, but from this point on, I won't tell you what standard conditions are on a test or a quiz or even the AP exam. So that tells us what our temperature is. It's actually at 25 degrees, which is 298 Kelvin. Our delta S is right up here in the previous part of the question, so we already have that value given to us. What we do not have is our delta H. So we need to find out what the enthalpy is. So what we need to do is calculate for delta H. And we do have all the information to help us calculate for delta H for the reaction. So let's do that. All right, so calculating delta H, again, delta H is the products minus the reactants. So we can go ahead and plug in our values from the given information from the table above, where the C2H6 has a negative 84.7 kilojoules per mole, and again, the units are given there for you. The C2H2 has a value of 226.7, and the hydrogen, again, under standard conditions, under the way that it exists at that temperature, it is already a gas, so it has no value because hydrogen gas is a gas, and it doesn't require any energy to make that into a gas at that temperature. So again, it deals with the elements, how they exist naturally at that state. So if I had solid hydrogen, which would be very, very difficult to have at that temperature, then it would have a value for heat of formation. So looking at the values where we take the products minus the reactants, and again, you don't necessarily need to show that value. I went ahead and did that just so that there was no question about where it falls into the equation. It equals a negative 311.4 kilojoules per mole. So that was worth 1 point. Actually going back up here to the point values that was assessed. Let's see, this was worth 2 points. You had 1 point for the correct answer and then 1 point for the stoichionomic relationship there. So getting back to that one. Also, you had 1 point for the heat of formation, or sorry, the enthalpy here for the reaction. But we haven't answered the question yet. We haven't answered what this value here is. Let's see. So let's go ahead and move that down. Let's solve for this. Whoops, come back here. So now that we know what our delta H is, and we know what our T and our delta S happen to be, let's plug that in. Also, we have to have like units, so we need to change our delta S from up here. Let's go ahead and do that real quickly. So if we have a negative 232.7 joules, so negative 2, sorry. Let's go back, negative 232.7, can I move you? Yeah, I won't. So if we have a negative 232.7 joules per mole Kelvin, probably would be a little better set up like this. Joule mole Kelvin. Then we know there's 1,000 joules in a kilojoule. And don't forget that. I know one student that actually missed 2 points because of that incorrect conversion, which gave the wrong answer to the delta G and also gave the wrong sign on the delta G. So not what you want to have. So negative 0.2327, and that's kilojoules per mole Kelvin. Now, the reason why we have to do that is because when we subtract down here, we have to have like units. So we have to make sure that everybody is on the same page. And generally speaking, we want delta G and delta H to be in kilojoules per mole. So it's just easier to change that than to change multiple things. So know that. So we have a negative, let's see if I, we're okay. So let's go ahead and input that, or actually go ahead and input our values, so Kelvin. So we actually have that extra unit there so that these can cancel out, which is nice because we don't want Kelvin in the problem, but it is in the equation. So now that we have our kilojoules per mole, then we can just solve. All right, so when calculating all this out, we get a value of negative 242.1 kilojoules per mole. So that would be your second point. The third point would be from answering the second question that says, what does the sign on the delta G indicate about the reaction above? So in this case here, since we have a negative delta G, that means that the reaction is spontaneous. More correctly stated, it is more thermodynamically favorable to occur. So what that means is that, yes, when we actually have our C2H2 with hydrogen gas, it will form that without us having to put any effort into it. So that will take place. So this is a spontaneous or a thermodynamically favorable situation. Okay. So now we have some more information. We actually have a delta H and we have a delta G value, and we have our delta S for the reaction if we need it. Okay. So let's look at part C. Calculate the equilibrium constant K for the reaction at 298. So again, even though this came later on in the problem, that should have been a heads up for some of you if you were stumbling with the temperature to use back in part B. So the equation you want to use for this one is on your equation sheet. It's delta G is equal to negative RT natural log of K. Now, there's a couple R values. The R value you do not want to use is the one for gases. How do you know which one's for gases? Because it says the R that we wish to use for this one actually has the energy unit joules within it. So the R that we want to use for this one, and it was stated in the video, is the 8.31 joules per mole Kelvin. Okay? So you have to look at the values for the R value when working with gases or working with thermodynamic type questions. So this R would be for this one because we have a delta G situation and we're not looking for pressure. All right, so let's plug the values in. We're looking for K, so we know everything except for K. So it's probably not a bad idea to rearrange this equation. Okay, so we're looking for the natural log of K. Natural log of K in this case would be equal to delta G over negative RT. Also keep in mind that your R value is in joules, so we have to make that conversion again. So your 8.31 joules per mole Kelvin needs to be switched to look like this, where we have 0.00831 kilojoules per mole Kelvin. So we have to have like units whenever we're working with these types of problems, okay? We can't divide unlike units and expect them to cancel out since we're looking for a K here. So, let's see here, let's move you down just a little, okay? And let's plug in our values that we do know. So the G we just found, which is right there, the negative 242. The RT we just found, so a negative sign there. And again, that's in kilojoules per mole Kelvin. And the temperature is at 298. So again, the kelvins cancel out, and we get an answer. Positive 97.6. And really it doesn't, well, the units cancel out. All the units are gone. So this is the value that we have. Positive 97.6, somewhere in that ballpark. So to find out what the value for K is, all right, so here's my value. I have natural log of K is equal to a positive 97.6. I need to take the anti-natural log of both sides. So what I'm going to do is I'm going to take this and this. So when I do that, then my equation looks like this. So the anti-natural log of the natural log of K gives me K, and then the anti-natural log of positive 97.6 gives me a really big number, which is around 287 times 10 to the 42, I believe. Yeah, times 10 to the 42. Now, there is no unit on this. So, and I had a couple people make a comment on their quiz saying, wow, that is a really big unit. Well, you have to remember that if something is spontaneous or thermodynamically favorable, and it favors the formation of the products, there's no such thing as too big of a value. Now, technically speaking there is, but that's not a big value for us. Because we've even seen exponents that have been in the negative 30s, so why freak out over something that's a positive 42? That just means that it forms a lot of products and there's not many of the reactants left over. And some may even argue that that represents a very strong reaction, which is okay, nothing wrong with that. All right, so let's look at the last one, which seemed to be the really fun question for a lot of you. The question says, calculate the value for the triple bond in the carbon in the C2H2 in kilojoules per mole. So the first thing you would like to do, probably should do, is write out the Lewis structures for all these. So I'll do that real quickly. All right, so here we have the Lewis structures. Now let's identify the different types of bonds that must either be broken or formed. So all of these bonds will be broken, and these will be the bonds that are formed. So let's do that. Okay, so here are the different types of bonds that either need to be broken or need to be formed. So looking at this compound here, we have two carbon-hydrogen bonds that need to be broken. So we need to consider those two bonds that are being broken. There's only one of these, and actually this is what we're looking for, so don't get too hung up over that. Since there's a 2 in the overall balanced equation for the hydrogen, that means that there are 2 of these bonds that we need to break. Coming over here and looking at the ethylene, we have 1, 2, 3, 4, 5, 6 of these bonds that need to be broken, and we only have 1 of those. So in this case here, knowing how many and what type of bonds we have and need to be broken is very important. So now what we can do is we can do our equation. So we know, and there's a couple ways you could do that. You could do the equation that does this. It says, okay, looking at delta H, which is bond energy, and that is equal to the sum of the reactants minus the sum of the products, okay? So that is the information that we know. This, unfortunately, is not on the equation sheet. I don't know why they don't put it on the equation sheet, but they don't. So when we look at delta H, we have to remember that the bond energy for making and breaking these bonds, for breaking these bonds and making these bonds, is the same amount of energy that's needed for the reaction to proceed forward. So what we need to do is realize that, okay, well, we calculated the delta H for the reaction earlier on. True, this is for the heat of formation for those reactants, but this is the heat for the total reaction. So we have a negative 311.4. So negative 311.4 kilojoules per mole is our heat of formation, or actually our bond energy. And then to find out the reactants, what we need to do is we have, let's just write them out. All right, so here's our equation before I plug any numbers in. So there's my total heat for the reaction. And again, I have two of these CH bonds. I have my one triple bond that I'm actually looking for, and I have two hydrogen bonds that will be broken. I have one carbon-carbon single bond. I have 6 carbon-hydrogen bonds. So let me now put the values in for each of these. So here are the values that we have for all of this. And let's go ahead and do another step. And so after adding up all the values inside, these are the values that I now have. What we really have is negative 311.4 kilojoules per mole is equal to a negative 1131 kilojoules per mole plus our carbon triple bond, carbon-carbon triple bond. So what we can do is we can add the negative 1131 to both sides. And then our carbon-carbon triple bond is equal to a positive, looks like, positive 820. A positive 820 kilojoules per mole. Now, I would dare say that for the majority of you, none of this was extremely difficult. I know that you all know how to do Lewis structures, and I gave you plenty of time to work out this problem. I probably should have only given you like maybe 20 minutes max, but I gave you well over 30 minutes to work this out. So I apologize for that. But under these circumstances, there's a lot of different skills that are involved here. The Lewis structures, knowing the concepts behind if you have a negative delta G, what that actually means, knowing the values for standard conditions, understanding that we have values for reaction versus for individual compounds or molecules. So again, read the question carefully before you just dive in head first and try to solve it.